we discussed the alpha decay, and here is where we were left. Just to remind ourselves that an important aspect of the alpha decay is that the daughter nucleus that forms after the parent nucleus checks out an alpha particle is a new element, and this phenomenon is called transmutation of elements. And we also said an important aspect is that, of course, the conservation laws are observed, and we have conservation of charge that has to do with the number of protons, so the atomic number at the bottom of the elements, and also the number of nucleons, mass conservation, in other words, is conserved. And this is how we can apply those two laws, the conservation of charge and the conservation of nucleons, to figure out what is the daughter nucleus. So after the alpha decay, we are going to see now a couple of examples from beta decay, a couple of types of beta decay, which similar aspects are involved. But let's discuss it one step at a time. So there are different types of beta decays, not just one type. So we are going to discuss the beta minus decay, which is actually a beta minus particle is actually an electron as we know it, but this electron does not come from the orbital electrons in an atom, it comes from within the nucleus. So anyway, the beta decay is actually an electron that is checked out by the nucleus, and that is why we call it beta minus. It involves a negative particle. There is also a beta plus decay, which, as you can it's easy to figure out that this is actually the opposite, a positive particle emitted, and in this case it's a positron, which is like the antiparticle of an electron that is emitted again by the nucleus. And these two types of beta decay we're going to discuss. The beta minus decay is when there are too many neutrons in the nucleus, and that is why the stability is not very successful. Too many neutrons, and therefore the nuclide actually tries to reduce the number of neutrons by changing one of the neutrons to a proton. In fact, we're going to see that this reaction is actually a matter of a quark changing. But nevertheless, we can see it as an attempt to change a neutron into proton. So this is about too many neutrons result in a beta minus decay. Obviously, the beta plus will be the opposite, too few neutrons. When a nucleus has too few neutrons to establish some stability there, then it decays by beta plus emission, which is like the opposite. A proton will change into neutron to increase the number of neutrons. So here we have the beta minus decay. Let us read what it says here in our text. If a nucleus has too many neutrons, it becomes more stable by emitting an electron. We also call this electron a beta minus particle because it has nothing to do with the orbital electrons. This one is produced inside the nucleus. It is as if one of the neutrons changes to a proton by checking out an electron, and we can write this as a reaction like that. The neutron, and note it's a charge and nucleon number. Charge because it's a neutron, it has a charge of 0, we assign it the charge of 0. And of course, a neutron is a nucleon, and its nucleon number is 1. So this neutron can change into a proton if it checks out. Here's the electron. And also there is an anti-neutrino that is emitted. It shouldn't say this neutrino is simple. Its symbol is this one, like V, which has a mass of 0 because it's a very small particle and smaller than an electron, and charge 0 as well. So both of these numbers, charge and nucleon, are 0. And the slash on top of the symbol means that this is not a neutrino, but an anti-neutrino, the antiparticle of the neutrino. Yeah. there's no need to call it electron neutrino. Obviously, it's the electron neutrino. What can it be? The tau neutrino. Obviously, this is the electron neutrino because we're dealing with particles from the first family, which our universe seems to be made of. So any neutrinos will be the electron neutrinos. All right. So there it is. It's like a neutron changes into proton by checking out an electron, and in the process, there is also an antineutrino that is emitted, and we know we have to add it there because of the conservation of energy. There are many conservation laws that have to be observed in a reaction, in a nuclear reaction, much as in any other reaction, like in chemical reactions. And one of them is the conservation of energy, and that is how we figured out actually that there is another particle there emitted, the neutrinos or antineutrinos. All right, so we have to include it there. Okay, and what we said now, it is nuclides that have too many neutrons that decay by beta minus emission. Like an example would be, for example, the carbon-14, which is a radioactive nuclide of carbon-14. This one is an example of a nuclide that emits a beta minus particle that decays by beta minus emission. So what happens here? Like say that we didn't know that its daughter would be nitrogen. Say we have the carbon-14, obviously it's atomic number 6, and we know that it decays by a beta minus emission. So it will produce a daughter plus a beta minus particle, which I prefer if we write it as an electron here, so that we know that it has a charge of -1 and the nucleon number 0. And okay, this antineutrino, we have to include it, which both its numbers are 0 here, so it's not a big deal to include it in our calculations. Now let us see, how do we find the daughter? This will be the daughter, the unknown daughter. Obviously, we have to write again the conservation laws for charge and mass. For charge, we have on the left-hand side, the carbon has a charge of 6, the 6 protons, in other words. 6 must be equal, we're talking about relative charge here. 6 must be equal to the charge on the right-hand side. So what is say that this is, what must we call it, X? Let's call it X, and this Y. What is this? X plus -1, the charge of the electron, plus 0. And therefore, if we solve now for X, what would be the X? That would be 6 -1 plus 1, isn't it? I hope I get it right. And which is 7. So this X, now this one is 7. We found that this is 7. Let's replace it with a 7. And as you can see, now that we have the 7, we know which element belongs to, because 7 can only be nitrogen, nothing else. And of course, remember, we need our periodic table to remind us which element corresponds to atomic number 7, which is nitrogen. Now to find the nucleon number, the mass number of this nuclide that is formed, again, we take the conservation of nucleons. So 14 on the left-hand side must be equal to all these numbers, this plus this plus this on the right-hand side, which is Y plus 0 plus 0, which means that this Y is also 14. So the nucleon number of this daughter formed is also 14, and as you can see, it's there, 14 up there. So this number up there, the mass number of the daughter nucleus that is produced, is 14. And therefore, this is how we know, well, the number 7 tells us what element this is, which is the nitrogen. And this is how we find that this daughter nucleus is a nitrogen. And as you can see, the daughter nucleus is different from the parent. This was carbon, now we have nitrogen. Again, we have transmutation of elements, you see? So again, there is transmutation of elements that takes place during a beta decay. Yeah? So transmutation of elements takes place not only from alpha decay, but also from beta decay. Okay, here we had the beta minus, but the same applies to beta plus. Let's see. Here is the beta plus, which is, as we said, is the production of a positron, which is, a positron is like a positive electron. It's an electron in all respects, except that it has a positive charge, the antiparticle of the electron. And by the way, if an electron collides with a positron, the two will annihilate one another. Anyway, so beta plus decay now, let's do it systematically and properly. If a nucleus has too few neutrons relative to its protons, it becomes more stable by emitting a positron instead of an electron. The positron is just like an electron, but with positive charge. It's very important, but the same charge numerically. It is the antiparticle of the electron. This type of decay is also a beta decay, and we can call the positrons beta plus particles. In this decay, it is as if one of the protons in the nucleus changes to a neutron by checking out a positron, like that. So, what do we have here? Let us see, okay, this is like a positron, what is the proton from a nucleus changes to a neutron to increase the number of neutrons by checking out the positron. And what type of nuclide we can use as an example? Here we have the nitrogen 13. It's a type of a nuclide that is most likely to undergo beta plus decay. Because look at this, it has 7 protons and 13 nucleons altogether, which means that it has 7 protons. And how many neutrons does it have? 6, isn't it? 6 plus 7 makes 13 altogether. So you see, in this range, this is a small nuclide. It has an atomic number less than 20. It's only 7. And for nuclides less than, with atomic number less than 20, if you remember, we had said previously, in order for them to be stable, they are stable if they have relatively the same number of protons and neutrons. And you see this particular nuclide here has less neutrons than protons, and therefore it's not stable. And what happens is that one of the protons changes into a neutron by checking out a positron to make the new nucleus more stable, to produce, in other words, a species which is more stable. So this one will change, it will become a different, it will produce a daughter nucleus, the new daughter, plus the positron, plus the neutrino in this case. But be careful now, look at this. This is a neutrino, not an antineutrino. You see, when we have the production of an electron, this comes out with an antineutrino. But if we have a positron coming out from the nucleus, then we have a neutrino, not an antineutrino. So this is a neutrino produced. Again, of course, its charge and mass numbers are also 0. And as you can see, look at this conservation of charge. 6 plus 1 is 7, which is 7, the initial charge number of the parent nucleus. And also the conservation of nucleons. 13 plus 0 is 13, which is equal to the nucleon number of the parent nuclide. And again, of course, we have transmutation of elements because the parent nuclide was a nitrogen one from an element, the element was nitrogen, and now we have a new element forming carbon. It's a carbon 13 that forms. This carbon 13 is not radioactive, so it will stay as carbon 13. It's not very common in nature because the common carbon is the carbon 12. but nevertheless, it's not a radioactive carbon, this one. So anyway, so the carbon 13 is more stable than the initial nitrogen 13. And there we have it, the beta plus decay. All right. Now, a third, let me read your message there. I don't understand anything covered on this topic. Can I kindly exit? You can exit, but tell me something though. Have you started? Yeah, it's not like starting from the beginning. It's have you ever tried? Have you started at all this topic? Or anyway, you can send me a message. Yeah. All right. So now the next thing is that the third type of decay. Oh, I don't have it there. Do I have it? Let me see. It's a gamma decay, but in the gamma decay, okay, I don't include it. We can talk about it. Doesn't matter. The gamma decay, it's obviously the nucleus does not emit any particle, but it just emits some radiation, electromagnetic radiation, in the form of gamma rays, gamma photons, and it reduces its energy. It drops to a lower and more stable energy level. So usually, the norm is that whenever a nucleus decays by alpha or beta emission, it also emits gamma rays in any case. So it's not necessary to, I mean, it's normal. Gamma rays is just emission of electromagnetic radiation in the form of the range of gamma rays, because they are emitted from the nucleus and they have more energy than the X-rays that are emitted by atoms. And simply, it's a drop of energy. It's not any particle emitted. So how, for example, if we have a nucleus which is very excited because it has too much energy, say the thorium, for example, here, thorium, this daughter nucleus. Thorium, since it was made out of the decay of the uranium, it's excited in an excited state, which means it has more energy than it should have. And usually we show it with a little asterisk on top to show that this is in an excited state. And what can this nucleus do? It can emit a gamma ray and it can drop its energy level. And you know, the lower the energy, the more stable the item is, plus a gamma ray. So we can represent this way the gamma decay. The gamma, we can, it's an electromagnetic radiation, but like the visible radiation or any other type of electromagnetic radiation, we can assume that these are photons, like a photon of light, because light, you know, has a dual nature. So if we consider this as a photon, like a particle of light of these particular frequencies or wavelengths, we can assume that it has zero mass and zero charge, of course, and this is how we can represent the gamma photon as a particle. So you see, because these numbers are zero, the daughter, if we can call it a daughter, the product of this decay, is not a different element from the parent. You see, the parent was thorium, the daughter is also thorium. It doesn't even worth to call it a daughter because it's the same element. It just has less energy and it's more stable simply because it has less energy, because some radiation, some energy was chucked out, emitted by the emission of gamma radiation. So there's nothing special about the gamma decay. But this is how we can represent it nevertheless. Now that we have spoken about all the three important decays that we need to know, and especially we know how to find the daughter by observing the laws of the conservation of charge and conservation of nucleons, we can try some examples from past exam papers, isn't it? And remember that we also need the periodic table here. So I have some questions to see how this radioactive decay appears in exams. Usually it's a part of questions that involve both electricity and radiation, like this one. This is from 2018, an example. Like you see, it's question 5 from this paper. It starts with electric fields and electricity, and then it continues. Look at this. There is an alpha decay here. So let us see what this problem says. It's nice to mix the problems. We can revise our electricity as well in this way. So actually, let's make this bigger so that we can see. State what is meant by an electric field. Yeah, well, it's just definition, obviously, for 1 mark. We have to say that the electric field is a region of space where a force acts on a charged particle. So this is what they want us to say, region of space. Yeah, not that it's the best definition, but anyway, region of space where a charged particle experiences the electric force, where charged particle or a charged particle experiences a force, the electric force, not just any force, experiences the electric force. Okay. What is the next question? A particle of mass m and charge q is in a uniform electric field of strength E. So uniform electric field. Remember, the uniform electric field can be represented with lines parallel to one another at equal distances, where the field has the same value at every point in space within this uniform electric field. Okay, so the particle has acceleration A due to the field. Okay, so this particle of mass m and charge q obviously moves and accelerates, and it has this acceleration A due to the field. Show that the acceleration of the charge is given by this formula. Okay, how do we start? This acceleration, actually, the acceleration is very common, I see, in this type of questions. And how do we start with this? First of all, we have a uniform electric field and a charge in it. So in general, what is the formula that gives us the electric field? What is the electric field? Is force per unit charge, isn't it? The general formula for the electric field is force per unit charge. So from there, we can solve for the force. The electric force is E times Q if we solve for force. Now we need this equation because when we have acceleration, the acceleration always links to a force, isn't it? Remember Newton's second law. So remember now that force is also m times a from Newton's second law, isn't it? And here where we can start linking now the acceleration to the force and the force to the electric field and the charge. So from here, as you can see, what do we have from there? That means that E times Q equals with MA, because we're talking about the same force here, isn't it? So now look at this. There we have the acceleration A linking to all these quantities that we are given. So if we solve for A here, we can see we get this formula. So this is E times Q divided by M, and here is our formula there. So this is how we show it. All right. The next question now, it's there we go to the radioactivity. A stationary nucleus X. A stationary nucleus X decays by emitting an alpha particle to form a nucleus of plutonium-240 as shown. All right. Determine the number of protons and the number of neutrons in nucleus X. in other words, the parent. Now they give us the daughter and they want us to find the parent. Okay, no problem. You see, what is the alpha particle again? We remember it's a helium-4 nucleus. So we need these numbers so that we need to write down the conservation of charge and the conservation of nucleons. So okay, let's the plutonium and the helium. This is 2, this is 4, this is 94, this is 240 given. All right. Now 94 plus 2, this is the 2. 94 plus 2 is 96. So this is the atomic number of our parent. So this is 96, and we can go straight to the periodic table and find out what's 96. What is 96? Where's 96? It is curium. Okay. So this is a curium nucleus. 96 from Madame Curie. Yeah? Okay. Now well, they don't ask us to find what type of nucleons this is. They just they want us to find just those numbers. So the number of protons is 96. We found it. Now the number of nucleons. The number of neutrons. Anyway, we have to find the number of nucleons first before we find the neutrons. So the number of nucleons is 240 plus 4. 240 plus 4 is 244. So this top number here is 244. Okay, so we can also write it up there. Now to find the neutrons, you say this is the total number of nucleons. This is both neutrons plus protons, eh? And this is only protons. So in order for us to find the number of neutrons, they try to trick us again. We have to subtract 244 minus the number of protons, which is 96. And what is this? 148. 148 neutrons. So the number of neutrons is 148. Okay, because this is the total number of nucleons minus the number of protons gives us the number of neutrons. All right. Good. Now, the next, what does it say here? The total mass of the plutonium nucleus in the alpha particle is less than that of nucleus X. Okay, they say that the total mass of plutonium and plus the mass of the alpha particle is less than the than that of nucleus X of the parent. Explain the difference in mass. And well, now to explain the difference in mass, we need to know that, strictly speaking, very often in the nuclear reactions, it's not the mass in grams that is conserved, as we learned from the classical mechanics, the Newtonian mechanics, because in nuclear physics, sometimes we have to accommodate the fact that mass and energy, mass can convert to energy somehow, and vice versa, energy can convert to mass. For example, if we measure the mass of 4 nucleons, for example, separately, say 2 protons and 2 neutrons separately, we add their masses, we find a certain mass. And then if we find the mass of a nuclide consisting of these nucleons, like an alpha particle, for example. Look at this. Here we have an alpha particle. The alpha particle consists, the nuclide of helium-4 consists of 2 protons plus 2 neutrons, isn't it? But these are joined together to a nucleus. Now, if we measure the mass of the nucleus of helium-4, we see that it's less than the mass of separate 2 protons and 2 neutrons. Because when these two come together to fuse together to form a nucleus, a lot of energy is released. And this change in mass that we measure, it's actually equivalent to this energy that was released when this nucleus was formed. And it's because of mass and energy together need to be conserved from Einstein's famous equation mc squared, isn't it? That represents this equivalence between mass and energy. So the mass of a nucleus of helium-4 is less than the mass of its separate nucleons, because when it was formed, some energy was released to the surroundings, and this energy released is equal to the missing mass of the nucleus. Now this part is not actually part of the AS level, so why do they ask that? Anyway, what can we say here? Conservation of mass and energy. Mass change is seen as energy. Nevertheless, these are actually from the A level, not the AS level. Energy is released as gamma radiation. We can say that when this parent nucleus, it's past 12, decayed, some of the energy was released as gamma radiation, and this is where the missing energy can be accounted for. And also we need to know that these two actually have a lot of kinetic energy. So that's enough. We have to stop because it's past 12. Oh dear. All right. So next week we can do some more problems from past exam papers. Okay. Next. Keep well in the meantime.